Hey everyone, today let's discuss the phenomena photoelectric effect. So here we have two characters, photo which implies the light and electric something related to electrons. So here the light is interacting with electrons. This can be defined as the emission of electron from the surface of a metal by the action of a beam of electromagnetic radiation. Let me tell you in detail. Sometimes light seems to act as a wave, and sometimes light seems to act as a particle. And an example of this particle nature would be the photoelectric effect as described by Einstein. So let's say you had a piece of metal, and we know the metal has electrons. And this electron is bound to the metal, that is, it is bound to the positive charge in nucleus. If you shine a light on the metal, so the right kind of light with the right kind of frequency, you can actually knock some electrons loose, which give a current of electrons to flow. So this is kind of like a collision between two particles, and the light particle is known as a photon, and this is massless. And photon is going to hit this electron, and if the photon has enough energy, it can free the electron, right? So we can knock it loose. So here we have shown the electron being knocked loose. This freed electron is usually referred as a photoelectron. So one photon creates one photoelectron. Now, what happened to the energy of the photon? That is the energy that went in. Some of the energy is needed to free the electron, right? Since the electron was bound to the metal, and some minimum amount energy is necessary to free the electron, and it is called as work function. And this work function differ for different metal. And the remaining energy of the photon must have gone into the kinetic energy of the photoelectron, which is freed now. And let's say the energy of the photon is h nu. So we can write h nu is equal to k plus w. That is, the total energy of the photon is used as a work function and for the kinetic energy of the photoelectron. This ejection of electrons can happen only if the photon of the right kind incident on the metal, which means the photon should have a minimum frequency below which the photoelectron emission is not possible, and this frequency is known as threshold frequency. So if the photon possesses a frequency lower than the threshold frequency, no matter what the intensity of this photon, it cannot eject a single electron from the metal surface. And if the photon possesses a higher frequency than the threshold frequency, this ejection can happen, and the number of ejected electrons is directly proportional to the intensity of the light. And this number of ejected electrons does not depend on the frequency of the light. But the photoelectron's kinetic energy is determined by the frequency of the light, not the intensity of the light. That is, with what velocity the photoelectrons are moving is determined by the frequency. According to classical physics, this experiment is explained as the electron in the metal would keep on absorbing energy at a continuous rate until it gets sufficient energy and then get ejected. This conclusion disagrees utterly with experimental observation. If this argument is to hold, then when using a very weak radiation, the photoelectric effect would not take place for a long time until an electron gradually accumulates the necessary amount of energy. But when the experiments were conducted with a light source that was so weak, it would have taken several hours for an electron to accumulate the energy needed for its ejection. but we could say that some electrons left the metal surface instantly. Further experiments showed that an increase in the intensity alone cannot eject the electrons from the metal, but by increasing the frequency of the incident radiation beyond this threshold frequency, even at very weak intensity, the emission of electrons starts immediately. So these experiment facts indicate that the concept of gradual accumulation or continuous absorption of energy by this electron as predicted by classical physics is incorrect. We know that Max Planck introduced a concept of the quantization of energy, and using this concept, Einstein assumed that light is made up of particles called photons having an energy of h nu, and he could explain the dependence of photoelectric effect on frequency of the incident light, and this relation is given by the equation A is equal to h nu, that is, the energy of light is proportional to its frequency, and the scientist Millikan found the value for h, the proportionality constant, and it was equal to the Planck's constant. Many experiments have shown that light exhibits wave-like behavior, that is, light can be diffracted by an aperture or slit. However, the photon in the photoelectric effect that exhibits particle-like properties, and the photon in a diffraction experiments that exhibit wave-like properties are one and the same. This recognition forces us to conclude that light has a wave-particle duality, and depending on experiment, it can manifest as a wave or as a particle. I hope you have got a basic idea about the photoelectric effect. Thank you.